Let's introduce the field of fractions. The idea is you start with integral domain D. And throughout our development of the field of fractions, it's going to be convenient to think of D as the integers. That's the perfect example to keep in mind. So you start with an integral domain D. An integral domain has the cancellation laws. If A times B equals 0, then either A is 0 or B is 0. But what it does not have is multiplicative inverses. So you can't necessarily divide in an integral domain D. So we're planning on enlarging D, adding more things to the set D to create a field, to create a situation where we can divide. And that'll be the field of fractions. So if you start with the integers, the smallest field that contains the integers is the rationals. So how are we going to do this? We're going to mimic the rationals. We're going to kind of copy the addition and multiplication from the rationals and adapt it for an arbitrary integral domain. We start by letting this be an equivalence relation on pairs of elements in D, but I do not want the 0 element in the second coordinate. So these are all ordered pairs where I have two elements in the integral domain D, except the second coordinate cannot be 0. And I'm going to define an equivalence relation by saying that A comma B is related to C comma D if AD equals BC. Now what you should think here is A comma B is shorthand notation for the fraction A over B. And this equivalence is going to be equals C over D. Now, if you have regular fractions of, integers, then this relation would say AD equals BC. So that's where this equivalence relation idea comes from. So technically, to prove its equivalence relation, you have to prove it's reflexive, transitive, and symmetric, but I'm not going to do that. It's a routine verification. The reason why people define equivalence relations to begin with is really to think about equivalence classes. So equivalence relations break your set into pieces, disjoint pieces that have union the whole set, the equivalence class. So we're going to let bracket A over B denote the equivalence class containing the element A comma B. So that will be my field. My field will actually be the set of all possible equivalence classes. So let F sub D be the set of equivalence classes and I need to define a multiplication and an addition. So I'm going to define the addition A over B plus C over D. I'm going to define this to be AD plus BC over BD, which is exactly the calculation you would get if these were actual fractions and you got a common denominator. And multiplication will be defined similarly, just pretending like we have fractions. Okay, I claim that this field isn't indeed a field. So you have an addition, a multiplication, you have a set. To verify something's a field, there are a lot of details to check. And in fact, there are so many details to check, I'm not going to check them all. I wrote down on this page all the things that you need to do to verify that you indeed have a field. So we have this addition, this multiplication. You have to check, since we're defining the addition and multiplication on equivalence classes, and it appears as if the choice of representative affects our addition and multiplication, we need to first verify that addition and multiplication are well defined. Then addition has to be associative commutative. There needs to be an additive identity. You need to have additive inverses. You need to check multiplication is also associative commutative. You need to verify the distributive laws hold, and there needs to be a multiplicative identity and multiplicative inverses in the field. So there's actually 11 things to verify, and all of them are routine. All of them are routine, so I'm not going to verify them all. In fact, maybe I'll only check a few of them. Since I think this well-defined property is sometimes confusing to some students, maybe we'll check the well-defined property 1. So let me verify this one here. So to show that the addition is well-defined, here's what I'm going to do. I'm going to take maybe A prime B prime in the equivalence class containing AB. So I'm going to say take this, so take this element in here and take another representative C prime D prime in this equivalence class. Now what does that mean? This means that using the definition of equivalent, we have that A prime B should equal A B prime, and similarly, C prime D should equal C D prime. So the way to remember the equivalence relation is just to pretend like these are fractions and then cross multiply, if you will. So then watch this. What happens if I take a look at A prime D prime plus B prime C prime times regular BD? Well, you could distribute. We're in an integral domain, so it's a ring. All the distributive laws hold and so on. So this would be A prime B D prime D plus B prime B C prime D. Now, according to these identities here, I have A prime B is equal to AB prime. So I'll change this to AB prime, D prime D. And likewise, we have C prime D is CD prime. So this is B prime B, C D prime. Now I could factor out what's common here. I could factor out a B prime D, because a B prime, let's see here, B prime D prime, because B prime D prime is in both terms. And I'm left with AD plus BC times B prime D prime. This is actually what we need to do to prove that I have a well-defined map, because this shows, by the definition of equivalence, this shows that the element A prime D prime plus B prime C prime, comma, B prime D prime is actually in the equivalence class that I need it to be, AD plus BC over BD. Anyway, that proves that the addition is well defined. And all other 10 facts are similar in that if you just understand the definitions of what's going on, the proofs are routine. There's no huge surprises here. So I don't think I'm going to prove any more of them. However, maybe I should point out what the 0 is. So the 0 is the element 0 over 1, the equivalence class containing this. Additive inverses, the inverse, so minus AB is minus A over B. You could prove that that's an additive inverse. The 1 in the field could be the equivalence class containing 1 over 1, and multiplicative inverses. So the multiplicative inverse to A over B is B over A. B can't be 0 by the definition of the equivalence class being on D cross D star. So I'm going to claim that this at least justifies that I indeed have a field. Okay, so I have this field of fractions is actually a field. I'd like to finish this video by proving a second theorem. So here's another theorem. If D is an integral domain, and there's a field E, so I have a field such that D is contained in the field, then the field of fractions, FD, is isomorphic to a subfield of E. So we technically haven't even defined subfield. We've only defined subring. But a subfield is what you'd expect. It's a subset of E that's also a field. Okay, so here's the proof. Here's the proof. In order to show that FD is isomorphic to a subfield, I need an isomorphism. I need to have a homomorphism with certain properties. So I'm going to do this. I'm going to define a ring homomorphism from the field of fractions into the larger field that contains my integral domain by the following. I'm going to send the equivalence class containing AB, and I'm going to send it to AB inverse. I claim that this is a well-defined one-to-one ring homomorphism. That would prove the theorem. So unlike the 11 things I have to show in the past theorem, I only have 1, 2, 3, 4 things to show for this theorem. I need to show it's well-defined, I need to show it's one-to-one, and I need to show it interacts nicely. It's a homomorphism, both with addition and with multiplication. So there are 4 things to check here. Again, these checks are completely routine. So I'm not going to check them all. So why don't I just pick one of them and leave the others to you if you'd like. So I showed well-defined in the last example. Why don't I show that it's a ring homomorphism with respect to addition? So we verify that, let's see here, if I do this phi of a sum, then by definition of addition in the field of fractions, then this is phi of AD plus BC over BD. And by the definition of the ring homomorphism, this is AD plus BC times BD inverse. Now, I'm in an integral domain. An integral domain is a commutative ring. It's a commutative ring. So BD inverse is B inverse D inverse. And I could rearrange terms. I could put terms wherever I'd like. So AD BD inverse would actually simplify to AB inverse. And similarly, BC B inverse D inverse would simplify to CD inverse. And this, by definition, is phi of A over B plus phi of C over D as needed. So that proves the addition property. The multiplication property is similar. 1-to-1 is not difficult to show, and well-defined is not difficult to show either. So I'm not going to check all the details here either. I think that will conclude this video. This video introduced the field of fractions. We proved that it was actually a field, and it's in some sense the smallest possible field that can contain your integral domain D. Okay, wonderful.